In this video we're going to be talking about what happens when you have more than one possible Lewis structure for a molecule. So here we have nitrate, and if we draw the Lewis diagram, we find that we need to have one of the nitrogen-oxygen bonds be double, but there's no way to tell which bond should be the double bond. So we can place the double bond in any of these three positions. And so notice how all of these Lewis structures, they're basically the same. They have two single bonds and one double bond. All we did is shift the position of the double bond. So when we have more than one valid Lewis structure for the same molecule and they're all the same, you just shift the position of one thing, then we call that resonance. And these different Lewis structures are called resonance structures. So according to these diagrams, nitrate will have two longer single bonds and one shorter double bond. But in reality, nitrate actually only has one type of bond, and this bond that it has is actually somewhere in between a double and single bond in terms of length and strength of the bond. So none of these structures are actually correct. The correct structure for nitrate is actually an average of these three structures, because in reality it only has one type of bond, not two longer bonds and one shorter bond. And so this resonance is necessary because, remember, in the localized electron model, we assumed that electron pairs were localized either as lone pairs on the atom or as bonding pairs in the space between two atoms. But in reality, electrons are delocalized, which means they can move around the molecule. So, for example, in nitrate, the electrons in these bonding pairs are not confined to this area. They can move around and rearrange themselves to make three equal length bonds. And so we use these double arrows to show that these resonance structures, they combine and their average is the actual structure of the molecule. And so again, resonance can only be used for what's called equivalent Lewis structures. And equivalent means they have the same number of single and multiple bonds. So each of these equivalent structures has two single bonds and one double bond. So sometimes we have multiple Lewis structures that they follow the rules, but they're non-equivalent, which means they have different numbers of single and multiple bonds. And in these cases, to determine the correct structure, we have to estimate the charge of each atom using a system called formal charge. And so the formal charge is the difference between the number of valence electrons on the neutral free atom and the number of valence electrons that belong to the atom when it's bonded in the molecule. So to count the number of valence electrons that belong to the atom in a molecule, we say that lone pair electrons belong entirely to the atom they're on, while bonding pair electrons are shared equally between the atoms that share them. So for example, here are two structures of sulfate. They both follow the rules for Lewis structures, but they're non-equivalent. So this one has 4 single bonds, while this one has 2 single bonds and 2 double bonds. So to figure out which one's more likely, we have to find the formal charge of each atom in this structure. So let's start with oxygen. Oxygen, usually when it's in a free atom, it has 6 valence electrons. And so in this structure, you can see each oxygen has 3 lone pairs, so that's 6 electrons, and then it has 1 bonding pair. And so in bonding pairs, the electrons are shared evenly, which means each atom, the oxygen and the sulfur, each get 1 electron from this bonding pair. So in total, each oxygen has 7 valence electrons in this molecule. So the 4-mole charge of oxygen is 6, the number of valence electrons it has naturally, minus 7, the number of valence electrons belonging to it in this molecule. So the charge of oxygen is -1. Now sulfur in its natural state also has 6 valence electrons, and here it has no lone pairs and 4 bonding pairs. So it gets 1 electron from each bonding pair for a total of 4 belonging to it. So its 4-mole charge is 6 minus 4, positive 2. So now let's look at this structure. Here there are 2 types of oxygen. These oxygens will have different 4-mole charges because they have different number of lone and bonding pairs. So first let's look at these 2 oxygens. They have 3 lone pairs and 1 bonding pair. So they each have 7 valence electrons belonging to them. So their 4-mole charge is 6 minus 7, -1. And for these oxygens on the top and bottom, they have 2 lone pairs and 2 bonding pairs. So they each have 6 valence electrons belonging to them. So their 4-mole charge is 6 minus 6, or 0. And the sulfur has 6 bonding pairs, so it gets 6 electrons. So its 4-mole charge is also 0. So once we find the 4-mole charges of these 2 structures, to determine which one is the correct structure, we use 2 guidelines. The first is that atoms and molecules try to get 4-mole charges as close to 0 as possible. And the second is that any negative 4-mole charges in the molecule should be on the most electronegative atoms. So looking at these guidelines, we can determine that this structure is more likely than this structure, because as you can see, a lot of these atoms have 0 4-mole charge, whereas in this one, none of them has 0, and this one is +2, which is further away from 0. So most of the atoms have a 4-mole charge very close to 0, and also, as we expect, any negative 4-mole charges over here are on the most electronegative atom in the molecule, oxygen.